Alright everybody, we discussed classical equations and now we're going to analyze them one by one. In this particular segment, or rather series of segments, we are going to look at the heat equation, right? As the name recommends, it's looking at how the heat is distributed in a particular one-dimensional rod. That's what I have over here, right? That's what I will be able to solve. Before I go ahead and write the equation, which I already did, there are a couple of assumptions I want to highlight over here. So the first thing is the flow of heat within the rod takes place only in the x direction, and obviously I'm saying that this is x, right? Or I can write this in a compact form. Heat flux is only in x direction. The other assumption is the lateral or the curved surfaces that I have over here, right here is what I'm talking about, these regions, they are insulated. So I don't have any heat escaping from this lateral dimension, right? So let's write it over here. The surface is insulated. No heat escapes in radial direction. Okay. The next one is no heat is generated within the body of the rod, which is reasonable. Also, the rod is homogeneous itself. The rod itself is homogeneous. So let me combine them and say that no heat generation within the rod, and basically rod is homogeneous. The other thing is coming from heat transfer. I have, this is called the specific heat. Unfortunately, if you follow my videos from this fluid mechanics, you will see that this is called the specific weight, but that's what we call in the heat domain, we call the specific heat. And also we have thermal conductivity. Thermal conductivity, that's the capital K. Those are constant values, right? So these are constant values. But let me go ahead and write the equation, which I already did. But this is what you're going to K. But this K is a lowercase k as opposed to the capital K that I have for thermal conductivity. And this is called the thermal diffusivity. And I'll talk about this in a minute. But here's what it looks. Del x squared will be equal to del u del t. And you can see this is for 0, x, l. So these are my boundaries. And obviously t is going to be larger than 0. So if I look at this K, thermal diffusivity, and that's defined by this K, which I have up there, thermal conductivity, divided by the specific heat times the density. Okay, that's what it is. So also for this particular equation, I need boundary conditions to solve it. So let me give you some boundary conditions for us to get going. So let's call this boundary conditions. Now have u 0, t. Do you see how I write it over here? This 0 is the spatial variable, which is the x, and t I'm keeping as still a variable, right? But that's why it's called the boundary condition. So you have this, and I'll have L. If I scroll up there, you will see that the right hand side of the rod is called L. That's the length of it. And obviously t will be larger than 0 for this particular case. And I have an initial condition. It's just customary to define it at t is equal to 0. You don't have to, but we'll go ahead and do that. I'm going to say that this is going to be f of x. I don't know what f of x is. It can be any distribution because that's what I want to go ahead and find. Okay. So the approach that I've done will be very similar to what I covered. That's why I covered them. We are going to do the separation of variables and do our best to solve this. And the separation of variable will look like this. U will be equal to x, x, t, t, right? That's what we did. So from here, you're going to get del u del x. T will be constant. You're going to get x prime t, right? And if I have the second order, which I need for this particular equation, I'm going to have x double prime and t, all right? I also need, as you see up there, I need del u del t, and that will be x t prime this time around, okay? So if I plug this in to that equation, so basically the goal, what I'm doing over here is I'm just pulling this and plugging into here, and I'm pulling this and plugging into there. There's nothing really too fancy, okay? So I have x double prime t will be equal to x t prime, okay? And I did this in the previous video as well. What I will do is I will divide the both sides by k x t. The reason is I want to leave one side of the equation with everything with respect to x's, the right hand side with t, right? That's the goal. And if I do that, you will see k's will cancel for the left hand side. I'll get x double prime. I can't do anything about it. T's cancelled, so I'll get x double prime by x will be equal to t prime. That will stay right there. X cancel. I have to have k over here and a t. Okay, I had this conversation before. Just to remind you, this is only a function of x. This is only a function of t. So then, as these are equal to each other, they must be equal to a particular constant. Okay, and I'll call this a separation constant. And let's write it in another color. It's going to be the lambda, okay? So then if I go back and write these two equations are two separate equations, because that's the whole point of separation. X double prime plus, okay, that's why I have a negative over there. It will be 0, and the second one will be t prime plus k lambda t will be equal to 0 too, okay? Let's write the boundary conditions in this manner too, because that's what I need. So basically what I had is, let's go up here and take a look. I said that right here, at basically x is equal to 0, I have 0, and I have L is equal to 0, I have 0, and t is the variable. So if I rewrite that, I'll get myself something like this, right? X of 0, that's the first boundary condition, and t of t will stay right there because I didn't specify that, it will be 0, and I will have another one, L, t will be 0. This will be sufficient me to go forward. So now let's look at the very first equation over here, and let's rewrite it and analyze this. X double prime plus lambda x is equal to 0. I'm not sure you remember this, but I covered this. This is called the regular Sturm Liouville problem. Okay, I have a whole segment on this. I will actually post a link over here so you can visit that if you choose to learn more about it. But the approach that I take was I will have three separate cases. The first case will be if my lambda is less than 0, then I will also analyze lambda is equal to 0. I will also analyze lambda is greater than 0, and I'll apply my boundary conditions and see what I get. Okay, and I did this back there as well, but in order to highlight that this is a negative value, I have a square which is going to be positive, and I put a negative in front of it to ensure that I have a negative lambda. So when all said and done, I have x double prime minus alpha square x is equal to 0, and from here you can see that if I write the ancillary form, again it's in the video of Sturm-Liouville problem, but I'll get myself m square minus alpha square is equal to 0. So from here you get your x to be c1 e to the alpha x plus c2 e to the minus alpha x. I have to apply my boundary conditions. One thing I want to go back from the boundary conditions to here is you do realize that I can have either x0 can be 0 or t of t will be 0. But I'm not going to say t of t will be 0 because then the segment will end. I don't have anything else, it's not going to be a function of time. So that's not going to work out, right? So then I'm going to say x0 is 0, okay? Fairly reasonable assumption. And the second one I'm going to say xl is equal to 0. So why don't I apply this, the first one? If I do the first one, I'll get myself 0 will be equal to c1 e to the 0, right, plus c2 e to the minus 0. So from here you do get that c2 is equal to minus c1, right? Because as you know, this is 1, right? Alright, so that's what I get. Let's use the second boundary condition, x of L is equal to 0. So from here you're going to see, let's write it, c1 e to the alpha L plus c2 e to the minus alpha L is equal to 0. So c1 e to the alpha L minus c1 e to the minus alpha L is equal to 0. And I'm going to multiply both sides of the equation by e to the alpha L. So then I will get c1 e to the 2 alpha L minus c1, right? Because c1 times e to the minus alpha L times e to the minus plus alpha L will give me 1 is equal to 0. So let's write this way. In c1 parenthesis e to the 2 alpha L minus 1 is equal to 0. So in here, I can have this can be 0, but then that's not going to give me a solution that I want. I'm going to have e to the 2 alpha L is equal to 1. So then you get 2 alpha L is equal to 0. Alpha is a negative value, some kind of a number. So I'll get an L. It doesn't really make sense at all, right? So then this can't be 0. So the only way is then that C1 will be 0 over here. Okay, that's the only solution, reasonable, physically possible solution. I have C1 0. So if I have this one, that C1 is equal to C2 is equal to 0. So then I got x is equal to 0. So I don't get much from having my lambda to be a negative value. But I'm still not panicking because I have 2 more to go. I have this lambda is equal to 0, and I also have the lambda is equal to a plus value. So then let's do the second one, which simply says that this lambda is equal to 0. Actually, if I go back up here, right here, so you can see x double dot will be equal to 0. Okay, so what does this mean? Then my x will be c1x plus c2. I can use c1 and c2 because it was 0 before. So let's do the boundary conditions. I have x0 is equal to 0. So from here you're going to get, well, c1 times 0 plus c2 is equal to 0. This gives me c2 is 0. Everybody's seen that, right? If I do the second one, xl is equal to 0. 0 will be equal to c1 times l, right? So from here you can see as l is not 0, c1 needs to be 0. Huh, what did I get? Both c1 and c2 is 0. It's very similar to what I have accomplished back here, right? So, okay. So then the only option that I have to go forward is let's look at the case when this is larger than a 0. Lambda is equal to alpha squared, which is plus, right? So x double prime plus alpha squared x is equal to 0. So you can see from this ancillary form is m squared plus alpha squared is equal to 0. Well, let's write it m squared plus alpha squared is equal to 0. I got my m12 is equal to minus or plus alpha I, right? So if I go ahead and write this in the trigonometric form, I'm going to get myself c1 cosine alpha x plus c2 sine alpha x. We'll proceed. Let's look at the first boundary condition, which will say that c1 cosine of 0 plus c2 of sine of 0 is equal to 0. So from here, this cosine of 0 is 1, right? And the sine of 0 is 0, so I didn't get anything for this. This drops out. So I get myself c1 is equal to 0. Okay, I really hope that the c2 is not equal to 0, otherwise I don't get much, right? Okay, so c2 times sine of alpha L is equal to 0. Okay, so I can say if C2 is equal to 0, I will get myself, then the heat equation turns out to be the solution of it is 0 only. Okay, so that doesn't really make sense. So now I will go ahead and say that the sine of alpha L is equal to 0, and this should look very familiar to you because this is from Stern-Liouville problem. And in order for this to be accomplished, I have alpha L is equal to n pi. So from here, alpha n, nth of it, will be n pi by L, and this n will be 1, 2, 3 all the way, right? And we had a name for it, if you remember. We call this eigenvalue, right? And the corresponding function we call this eigenfunction. So from here, x of x, when all said and done, I will get myself c2 times sine of n pi by L, which is alpha, times x, right? That's what I have. So this is my eigenfunction. So this is the solution to the xx. Okay, let's go back and revisit this because it's been a long kind of segment, but I separated this into two. I looked at the very first equation, I'm done with it. Now I've seen that, okay, this is what happens, but I didn't really touch this equation, so why don't I go ahead and analyze this equation. But again, I only am going to look at when this is a positive value, because when it's 0, already this is 0, and it's 0, it's 0, so I'm only going to look at the positive, okay? So I don't have to do a lot for that. So let's change the colors, and we're going to have t prime plus lambda kt is equal to 0. And as this is alpha square, so if I could plug it in, I'm going to get myself n squared pi by L squared, right? Okay, so then what did I get over here? So, okay, it's a very simple equation, right? So let's write it t prime plus k n squared pi squared by L squared t is equal to 0. If I go ahead and solve this, it's a very simple first order ODE. I'll get my t to be c3, because I use c1 and c2, e to the minus k n squared by L squared t. So fairly simple. Note something over here. This is a function of n. Okay, so n will be 1, 2, 3, right? So I'm going to write this way. U of n, nth of it, x comma t will be xx tt. So that was the whole point why I did the separation of variables. And if I multiply this, I'm going to call this an. I'll explain, give me 1 second. E to the minus k n squared pi squared by L squared t times sine n pi by L x. Okay? So that's what I have for my un. So what is an over here? One thing that we have done is I call this C2 times C3, right? Because I had this over, where is it? Here C2, here is C3. Why didn't call it, I don't know, A only, an? Because it's a function of the n. I have n over here, I have n over here, right? And I'll make a point. I will go ahead and use my superposition principle, okay? The superposition principle says that if I have my un is given like that, I'll get my entire u will be the summation from n is equal to 1 to infinity, right? And the summation of these individual terms. So if I go ahead and write this, it's going to look like this. N is equal to 1 to infinity an. I'm simply writing as e to the minus k, let's do parentheses, n squared pi squared by L squared t times the sine of n pi by L x. Okay? And this definitely satisfies both of the boundary conditions, okay, that we have established. But there's one more thing. There's one more thing that we didn't really use. Let's go up here. I'll tell you right here. I didn't even touch it that, right? This was u x comma 0. So I was putting t is equal to 0 and x is the variable. And is f of x? I don't know what f of x is. That will be this information that will be supplied to me, okay? So if I go down here then, so initial condition, u x comma 0 will be, which is f of x, that's what was given to me. So if I'm looking over here, so I'm going to put t is equal to 0. When I look at t is equal to 0, this term will be 1. So that will be gone. Okay? So let me go ahead and write this. So infinite n from 1 to infinity, this is the summation sign. An, it looks simple. Sine n pi L by x. Okay? Okay, for some of you, you have already seen this. Right? So this is from what I've studied for the Fourier series expansion, and more particularly sine series expansion, half expansion. Okay, I want to just remind you what it was as with a different font. A0 was 0, an was 0, and my bn was 2 by p, integral from 0 to p, f of x, sine n pi x by p dx. While my f of x was given to me as summation sign from 1 to infinity, bn sine n pi by px. Now, let's look at these. Let's look at that. There is some similarity. So you can see now I don't have to do anything. So I can simply say from here that this is a Fourier series expansion, more specifically half-range expansion of a sine series. P, looking at it, is L. All right? And if I, so basically, by the way, you realize that this an is equal to bn that I have over here, right? If I go ahead and write my an, so an will be, which is bn over here, so I'm just simply going ahead and rewriting this, okay? So my an will be 2 by L, because p is L, 0 to L, f of x times sine n pi by L. What happened to p? It became L times x times dx. That's what my an is. So okay, so if I go back up over here again, then I can get my final. Now I know what an is. So my final equation will be this, except my an will be from down here. So I can actually combine this for one last time, and I can write a nice equation for you. This was the whole point why I covered the Fourier sine series, so it's going to make my solution so much more easier. Okay, n is equal to 1 to infinity from 0 to L, right? So let's put it in parentheses. So this is the an, f of x times sine n pi by Lx dx, so that's my an, times e to the minus k n squared pi squared L squared t times sine n pi by Lx. So this is the solution to the 1D wave equation, which specifically analyzes the heat transfer inside of a cylindrical rod. Okay. Once you have this, basically you're just going to look at this fx and plug in what is given to you. and so the rest is actually more mathematics oriented. Okay, I'll be right back. Thank you for watching this segment.